Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we are going to look at other vector spaces. In this topic we are going to describe vector spaces of discrete signals, of polynomials, of continuous signals, and of images. In each of these cases we will see that these vector spaces may have vectors that don't look much like our finite dimensional vectors, but they nevertheless still satisfy the 10 axioms of a vector space. A discrete signal is an infinite sequence of real or complex values, and generally in your calculus course you would refer to such things as infinite sequences. However, as engineers, it is better to think of it as a signal that we are reading about the real world. Now, in general, in engineering, discrete signals are represented by italicized lowercase letters such as x, y, and z. And so here, the discrete signal x may be a periodically sampling of a person's body temperature. Now, in general, the discrete signal x, you can describe or access the various entries of that signal not by using subscripts as within finite dimensional vectors, but rather with square brackets together with a number. Now, the reason that we start at 0 instead of 1 is because at time 0 is when the system is turned on. So such signals are readings from periodically sampled sensors or other periodically sampled data. And the reason that engineers model their systems with infinite discrete signals is because once you turn a system on, you may not be sure exactly when it may be turned off. And so you'd like to determine at which point may your system actually fail if you leave the system on for too long. Now, given the collection of all discrete signals, either real or complex, we can define the scalar multiplication of a discrete signal x as alpha x, where we simply multiply each entry of that discrete signal by alpha. Given two discrete signals x and y, we can add them together, which is just adding the corresponding entries of the two signals. There is, of course, the zero signal, and the zero signal is just equal to 0 for every single index. Now, we will represent an expression we intend to evaluate for every single index k by that value with a hat on top of it. So in this case, every single entry in this discrete signal is 0. We can also calculate an additive inverse. Given the discrete signal x, we can define its additive inverse negative x by simply negating each of the entries within that signal. Claim. With these definitions of scalar multiplication, vector addition, the zero vector, and additive inverse, the set of all discrete signals forms a real or complex vector space, again depending on whether or not the entries of these discrete signals are real or complex respectively. This shouldn't really surprise you. After all, if a 1 million dimensional vector is still a vector, there's not much reason you couldn't just go on to infinity after that. Now, this is beyond the scope of this course and something you will see in your upper year courses, but if the absolute value of gamma is less than 1, be it real or complex, then we can define the signal gamma to the n as being 1 gamma, gamma squared, etc. That is the kth entry of this discrete signal is just gamma raised to the power k. Now, these should look familiar. This is essentially a geometric sequence, and because the absolute value of gamma is, well, at least when it is less than 1, it is a geometric sequence going to 0. So, for example, 1/2 to the n as a signal is 1, 1/2, 1/4, and so on and so forth. Thus, if we were to multiply this by 0.4, it would simply multiply each of the entries by 0.4. Similarly, if we added these two signals, 1/2 to the n and -1/2 to the n, this is just the signal that has entries 1, 0, 1/2, 0, an 1/8, 0, and so on and so forth. So we can add such signals together. Now, for our next vector space, we will look at polynomials. Recall that a polynomial in X is simply a linear combination of terms, that is, x raised to an integer power, where that power is 0 or greater. Now, polynomials will be represented generally by lowercase Latin letters P, Q, and R, or in that range of the alphabet. Now, for example, P may be a polynomial. Notice that it is P that is the polynomial, not P of X. P of X is the polynomial evaluated at X. So, for example, this polynomial is a linear combination of x to the 5, x squared, x, and 1. And you can read off the coefficients there. Now, just to remind you, the degree of a polynomial p, denoted deg of p, or degree, is the largest exponent of a term within the polynomial that has a non-zero coefficient. So the polynomial of the polynomial above has degree 5. Now, polynomials are used by engineers to locally approximate real-world continuous functions. Now, given the polynomial p, which at an arbitrary value of x may be given as follows, then we can actually evaluate it by putting in an actual numeric value within the parentheses. Now, in general, an arbitrary polynomial of degree n is represented by a linear combination of terms where the coefficients are given. Now here, the coefficient of x to the n is alpha sub n. This can also be represented using summation notation. So this polynomial is the sum of alpha sub k, x to the k ranging from 0 to the degree of this polynomial. If it is ever asked what is alpha sub n, where n is greater than the degree of p, then that coefficient is simply given as 0. Thus we may define the following. The scalar multiplication of a polynomial p by a scalar beta is the polynomial which has each of the coefficients multiplied by beta. Vector addition. Well, given two polynomials, vector addition is essentially polynomial addition. So the polynomial p plus q is simply the polynomial that is the sum of the coefficients for each of the terms, where m is the degree of the sum, and this is going to be a value that is less than or equal to the maximum of the degrees of the two polynomials being added. The zero polynomial, represented by 0 cap, is simply the polynomial that is 0 everywhere. And the additive inverse of a polynomial p is negative p, and this is the polynomial that has the same coefficients but negated. So if the polynomial p is x squared plus 1, its additive inverse is negative x squared minus 1. Now, all polynomials are linear combinations of monomials with coefficients equal to 1. So here we see x to the n with a cap over it. This is the polynomial which, evaluated at x, is x to the n. So for example, if p of x is this polynomial, then we notice that it is simply a linear combination of these terms. So 1 times the first term, 0.2 times the second term, 0.5 times the third term, plus 0.9 times the fourth, which is 1. Now, claim. With these definitions of scalar multiplication, vector addition, the zero vector, and additive inverse, versus the set of all polynomials in the variable x forms a real or complex vector space, depending, of course, whether or not the coefficients are real or complex, respectively. Engineers will often represent the vector spaces of all polynomials in the variable x as the bold R with x in square brackets, or a bold C, again with x in square brackets, where the x is the variable in question. Okay, for our next vector space, we will be looking at continuous functions. However, as engineers, because you are going to be interested in those functions that describe the real world, that is, those functions that describe some aspect of the real world that can be measured and quantified, we will refer to such functions as continuous signals. Again, indicating that it is something that we can read and perhaps respond to appropriately. So, for example, given the continuous signal f, where f evaluated at a time t is given by this linear combination of exponentials. Here, the entries of this signal f are accessed by evaluating f at t for some value of t in the domain of, in this case, the non-negative real numbers. That is, t is greater than or equal to 0. Now, a continuous signal is a continuous function defined on some fixed domain where, in general, that domain may be all real values, especially if we're considering spatial variables, all reals greater than or equal to 0, generally temporal, where we turn the system on at time t equals 0, or all real values on an interval a,b, especially when we are dealing with periodic functions, in which case we will only consider that signal on one period, in this case ab. Now, in general, continuous signals are represented by lowercase Latin letters such as f, g, and h. So, for example, f evaluated at a time t is given by this scalar multiple times an exponential. And again, just to reiterate, in general, from the point of view of engineering, such signals are actual real-world measurable values that we are trying to deal with, either respond to or control. Thus, we may define the scalar multiple of a given continuous signal f is described by alpha times f, and it is the continuous signal which, evaluated at t, is just alpha times the original signal evaluated at t. For vector addition, given two signals f and g, their sum, f plus g, is the continuous signal which, if evaluated at t, is equal to f evaluated at t plus the g signal evaluated at t. So notice on the left-hand side we have the continuous signal that is the sum of the two signals evaluated at t, and that happens to be defined as the first signal evaluated at t plus the second signal evaluated at t. Of course, the zero vector is the zero function or the zero signal, and that just evaluates to zero for all values of x on the domain, be it values of x or values of t. And of course, for the additive inverse, given a continuous signal f, negative f is the continuous signal which, evaluated at t, is the negation of the signal evaluated at t. So, for example, here's a signal f where f evaluated at t is given by e to the negative t. Here's that same signal multiplied by the scalar 0.7. This is the sum of two signals. The first is 1.8 times e to the negative 2t. The second is negative 0.8 times e to the negative t. Here we see that same sum and its additive inverse. And as you can see, if we add these two continuous signals together, we will get the zero signal. So, claim. With these definitions of scalar multiplication, vector addition, the zero vector, and additive inverse, the set of all continuous signals forms a real or complex vector space, once again depending on whether or not the values of those functions are real or complex valued, respectively. Now, recall that a discrete signal could have real or complex values, as shown here. Similarly, polynomials and continuous signals will be functions of a real variable x or t, but it is their values that may be real or complex. So on the left we have a polynomial with real coefficients, and on the right a polynomial with complex coefficients. On the left is a polynomial which is real, and on the right is a polynomial that has complex values. It's e to the jt. So in general, engineers do not deal with complex domains. The domain will be the reals, the positive reals, or some sort of interval. It is only the range which, under certain circumstances, may be complex. Now, you may be used to referring to a polynomial p of x or a function sine of x. Please remember that there is a difference between the polynomial or a function and its evaluation at a point x or perhaps t. Remember that for finite dimensional vectors, the vector itself is just u. The value at the entry k is described by u sub k. Similarly, x is the discrete signal. X at the index k gives you the value at the index k. So, x indexed at k is a real value, or complex, whereas x itself represents the entire signal. Consequently, p is the polynomial. P of x is a real value. F and sine are functions. F evaluated at x is a real or complex value, and sine of x is, well, in this case, a real value. We're going to look at one final vector space. Recall that a black and white image, which is actually grayscale, has m by n pixels, each of which has an intensity between 0 and 1, 0 being black, 1 being white. If we remove the restriction on the intensity, allowing the intensity to be any real number, then we can think of such an image as a vector. For example, we can multiply the intensity of each pixel in an image by a constant alpha. We can add the intensities of two images together, or subtract one image from another. Basically, we would subtract the intensity of one image at that pixel from the intensity of the other image at that pixel. There's, of course, the zero image, that is, the image that is all black. And of course, there's a negative image where each pixel has the negative value of its intensity. However, now it comes to interpretation. Now, you may want to think of an image as a matrix because it is square, but it's actually more clearly a vector. So important for images. Just like there's the vector space of 5-dimensional real vectors and 8-dimensional real vectors, and these are two different vector spaces, so too are the vector spaces of 1024 by 768 pixel images and the vector space of 3840 by 2160 pixel images. So the vector, we would only consider, for example, the vector space of all 1024 by 768 pixel images. We would not ask what happens if you add a 1024 by 768 pixel image to a 3840 by 2160 pixel image. So now, if pixels can now take on all real values, you would then have to interpret such an image if you're trying to display it to the screen. In general, what you're probably going to do is have any intensity that is greater than or equal to 1 to be represented as white on the screen, and any negative intensity, or 0, is going to be displayed as black. Alright, in summary, in this topic, you now understand that there are many other vector spaces. The ones that engineers care about are discrete signals, polynomials, continuous signals, and images. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!